Greetings. I am Vinod Vasan, a student of Mechatronics and Automation. And today I shall be talking about convolutional neural networks or CNN as a deep learning strategy. First of all, it becomes important to understand what is artificial intelligence, at least a quick glimpse of it. In the grand scheme of things, artificial intelligence is essentially a computer's capability or the capability of a computer system to be able to emulate or mimic the cognitive capabilities and abilities of a human being, in addition to being able to solve problems that humans constantly encounter as per requirements. So that's what AI or artificial intelligence or as a branch of study is all about. Artificial intelligence in computer systems is recognized through machine learning. And machine learning essentially involves providing a computer system that capability to learn, to acquire information or knowledge, so to speak, and extrapolate that learning over the data that is in turn fed to it. So at the end of the day, it is essentially a pathway to enabling or towards enabling a computer system to make data-driven decisions. That's what machine learning is about in gist. So where does neural networks come into play? Where do these entities come into play? So moving on, throughout the course of this presentation, I shall be touching certain key aspects of the field of artificial intelligence, especially or more particularly in the field of deep learning. So we'll be talking about what is the deep learning space all about, a quick overview of deep neural networks, and then we ask ourselves a principal question: why do we require deep neural networks or DNNs or neural networks at large? And how are deep neural networks different from traditional machine learning algorithms or different from applying traditional machine learning algorithms? We would follow that up with a proper insight into convolutional neural networks, the core of this presentation. There would be an insight and understanding of the key elements of CNN. There would be a discussion about or on a sample four-layer architecture of a convolutional neural network, CNN. And of course, there would be a high-level overview of the potential benefits and the current and prospective CNN applications and deployment. So this is a Venn diagram that essentially presents where deep learning effectively implements. So as stated earlier, artificial intelligence essentially involves giving a computerized system the ability to solve problems through the cognitive pathway that is originally attributed to rational sentient beings, such as human beings. So we've got to ask ourselves, well, is AI and machine learning exactly the same? Strictly speaking, machine learning is, as is evident, a subset of artificial intelligence, and thereafter, deep learning is a subset of machine learning as well. So deep learning or artificial neural networks fall under the broader umbrella of machine learning as a specialized set of algorithms. So when do we use machine learning and when do we use deep learning? So deep learning is a subset of a family of machine learning algorithms. That is evident from the subset here, from the Venn diagram. It effectively encompasses strategies such as deep neural networks, DNNs, deep belief networks, transformers, recurrent neural networks, RNNs, and convolutional neural networks, CNNs. So essentially speaking, the deep learning space falls under a broad umbrella of artificial neural networks. But why so? Essentially, machine learning models are data-driven. The decisions they take are going to be based on the input data that you give them, and thereafter they make their choices. In deep learning, we try to emulate the structure of the somatosensory constitution or the cognitive neural map of the human brain. So that's what deep learning space is all about. So if we take a deeper insight, neural networks are at the end of the day AI algorithms, and they emulate the functioning of human somatosensory systems, the perceptory systems, perception effectively. So we've got neurons, we've got synapses, and how much of a weight and how much of an offset or a bias must I attribute to each of these individual decision-making elements? That's where the concept or terminologies of weights and biases come into play. So neural networks are, yes, networks. And why are they networks? Because they're effectively nodes which are interconnected with one another. And biases and weights are in turn assigned to each node to determine, well, how much of a constitution or how much of an impact should this particular parameter have in my final outcome. But it is important to keep in mind that neural networks, deep neural networks, or you go with deep belief networks or convolutional neural networks, which we will be talking about, these are still machine learning approaches. They are subsets. However, the difference being that there is a bit more of an organic touch over a great depth, that is many layers of decision and feature understanding. Generally speaking, deep neural networks are feed forward in the sense the vast pools of data that is being fed into the neural network actually propagates in the forward direction. And neural networks are widely suited towards handling or widely suited for handling complex non-linear classification problems where the relationship between the input and the output is not necessarily direct and requires a lot of interpretation. So where do we apply neural networks? First off, it becomes important to ask ourselves, why do I have to choose neural networks over machine learning algorithms? In principle, machine learning algorithms or principle or approaches in general are advocated towards handling structured data. Structured data essentially refers to that data that can be searched, that can be quantified. It could be text or it could be wordings, for example. On the other hand, you've got unstructured data, data that can't necessarily be searched, such as music or pictures or a podcast or audio files, for example. So neural networks, deep learning networks specifically, or in a much more broader sense, rather, are suited towards handling this form of unstructured data. That's the first aspect. The second understanding is that neural networks at large have a much more robust feature engineering or feature understanding and interpretation capability, especially convolutional neural networks that are widely adapted for applications such as natural language processing, image classification, automatic speech recognition, and that can be seen from the screen here. So the benefits of machine learning and thereafter deep learning, the benefits are usually common. It's more of a question of what advantages does deep learning have over machine learning. That also takes the cake. So to start off with, the advantages of machine learning basically include the capability to handle large quantities of data. So handle variance of data is where deep learning comes into play. But when we talk about machine learning, being able to automate redundant tasks, handle large quantities of data in turn without having to pass every bit of information explicitly is what one of the major advantages of machine learning. When we talk about neural networks, there is a slight drawback in the sense that because of the amount of processing required to be done on account of the variety of features to be understood and thereafter decided upon, the hardware requirements would certainly be a bit more intensive. However, that is a trade-off that we would have to make if we desire commendable classification or decision performance. So the pros of neural networks include handling of complex and diverse data sets very well, sweeping over vast reserves of data during the learning process, compatibility in general with automation, and of course, with all these pros, one of the most important advantages of neural network, it does all of this whilst achieving a very commendable accuracy in performance or classification at large. So generally, we utilize such networks for solving either classification problems into either so you've got binary classification problems or you've got multiple class-based classification problems, and of course, regression-based problems also. So how are DNNs different from traditional machine learning algorithms? Three key points. First of all, the angle of attack or the modus operandi that neural networks adopt, the algorithm, so to speak, that is advocated by such networks towards solving a problem. You see, machine learning generally banks on traditional algorithmic approaches with mathematical touches, such as linear regression over reserves of structured data. On the other hand, a bit more organic learning approach through the emulation of neural constitution of the human brain is advocated by deep learning networks over unstructured and diverse data groups. That's the first aspect. The second understanding is the intervention of the operator, or so to speak, the programmer. Deep learning requires ample human intervention during the training and testing overview phase, but it can thereafter be deployed to operate in an unsupervised manner once the threshold performance is met, and thereafter once the configurations are made in that particular system so as to achieve the expected performance capabilities. The third advantage that DNN has over machine learning is its immense feature engineering capabilities. But it is also important to understand that there is a slight catch to this, in the sense that traditional machine learning algorithms effectively require an adequate feature engineering expertise on part of the user to realize it successfully, at least a decent understanding of how feature engineering works. But a high level understanding, or I would say a relatively restrictive understanding, would more or less be sufficient to deploy a deep learning model without having to really worry about the salient aspects of feature engineering or depths of feature engineering. Thereafter, the minimal domain expertise in feature engineering would more or less be adequate to deploy such models. So, what are convolution neural networks? So, as explained earlier, convolution neural networks falls under the broad umbrella of an artificial neural network. So it is a specialized deep learning algorithmic approach that is adapted for complex input scenarios, and I emphasize in visual imagery analysis domain largely, so to speak. It is also referred to as SIANN, that is invariant, in other words, invariant to spatial distortions, that is space. We'll have an understanding of what this is about in a while. So what do we mean by convolution? There is a significance to the image that's been enclosed here. A convolution is a mathematical operation wherein you overlay an individual or a given function over another function. An input image, for example, is the basic function. Let's say it's a basic input element rather than a function. So you've now got a feature detector, as can be seen here. We always call that as a filter or a kernel. When you take a filter or a kernel and you pass it or slide it all across the input image, for every position of the kernel, you get an output that is effectively an element in what is called a feature map, a resulting matrix. So you've got one input image and you've got one filter or kernel. And when the filter or kernel is made to pass along the entire distribution of the matrix, you get one effective output called as the feature map. So you can have multiple filters or kernels where each filter or kernel is designed to handle or at least detect a feature of a particular kind. It could be, let's say, detecting the whiskers of a cat, or you can have one filter towards detecting the distribution of certain patterns in the eyes of a cat, for example. So you can have a lot of such filters that can pass over an individual input image that gives you a feature map. So that's what's mentioned in the last point. Convolution neural networks adapt or adopt filters that are progressively optimized to suit classification requirements at the end of the day. So the key elements of convolutional neural networks are presented here. First of all, it's important to understand that CNN is layered. There are multiple layers. It's not just a single layer or not just a single mode of attack, but it's more of a teamwork rather. We start off with an input rather than a layer. Let's just call it an input. Uh, Images can be in this particular domain of understanding regarded as tensors, in the sense that they've got a height, they've got a width in terms of the number of pixels, so many pixels by so many pixels. And usually we use another terminology called as depth. Uh, Generally and most typically, depth refers to the color scheme that a particular image advocates. Normally, the depth is 1 for grayscale images and equal to 3 for RGB images, red, green, and blue. And N basically refers to the number of inputs, the number of input images that I may be feeding either as an individual unit, a single image, or as a batch. So the input that has been obtained, for example, 28 by 28 pixel image, would thereafter be passed on to the first convolution layer. But how? As we talked about earlier, we will have what is called a filter or a kernel. And for example, here, as can be seen, we might have a 3 by 3 kernel. And this 3 by 3 kernel or a filter that is adapted for a specific purpose might be 1 in number, or you might have 32 such kernels also. So each of these kernels will pass over the entire bulk of the input image and render a feature map. But because in this particular example, as we can see, we have a depth of around 32 in the second layer, that implies there are around 32 filters that are applied on this even input image that constitutes an output that is in turn depth of 32. And again, we have an output image of this particular, or an output rather, of the input operation that is 26 by 26 pixels long, or high and wide. But why is that so? Again, it's matrix multiplication, right? So if you've got a matrix of order m by n, and you are effectively multiplying it with another matrix that's of order, let's say n by p, your resulting matrix will be of the order n by p. So the same concepts over here, but there is of course a dedicated formula, each of which might be adapted for a specific purpose. You've got concepts such as stride. Stride effectively refers to, well, how is my filter or kernel moving all along the image? A fundamental question can arise, well, should my filter move piece by piece? So should it move only with steps of 1? Not necessary. You could have a value of stride equal to 2 or 3 or so on, and you could thereafter make your kernel move over greater steps or jump over a larger value. There is also a concept called padding, whereby you take an image and you have all these numerical data and you pad it or fill it with zeros, and you thereafter ensure there is no loss of data. There's an interesting observation we can make here. You see, an input image here has a height and width of 28 and 28. Thereafter is reduced to a height or a size of 26 by 26, and again 24 by 24, and then 12 by 12. So imagine having a convolutional neural network or any neural network where you've got n number of such layers. A general neural network, effectively speaking, has an input layer, an output layer. In CNN, you've got hidden layers in between. You've got, let's say, so many layers that is designed to handle millions and millions of learnable parameters. So what happens is that the input that you're providing is going to reduce to an extremely small dimensional provision. And that is not necessarily favorable as you move along. So you might want to counteract that effect by including a concept called as padding, whereby you might go from 28 by 28 to 26 by 26, but then you add some padding so that you do not experience that drastic reduction in dimension as you progress along the entire bulk or the length of the network at the end of the day. So this process is called as convolution. So once the first convolution has been applied, once the first set of filters have been overlaid on the input image, you get an output that constitutes the first convolution layer. You can thereafter have multiple convolution layers based on your requirement, so to speak, multiple hidden layers to constitute your requirement based on the depth to which you should extract these features, based on the characteristics of these features. It is important to understand that convolutional neural networks would be able to extract high level features also based on low level features. A very important assumption it in turn makes is that high level features are based on low level features. So moving on to activation function. So there is a certain concept of thresholding, right? You can't allow all values to permeate. So let's just say that you've got an image and this image has got dark lines all around it. So if you want to transit from an image with dark lines all around it, let's say the elements of the first convolution layer, we're not talking about the input image. We're talking about what are the elements in the convolution layer. We'll take every one of these inputs, which is extended through a depth of 32 in the convolution layer. I shall refer to the inputs of second convolution layer as the elements in CONV1, as can be seen here. So these inputs, rather, let's say they've got certain specific features, and each of these features can be represented by a number in a matrix. So an activation function is basically a mathematical function. For example, there is a very commonly used activation function called rectified linear units, or ReLU, that basically makes a very simple decision. It states that when any particular value, let's just say my matrix, is greater than 0, you just input that number itself. You've got a straight line graph, effectively, that passes through the origin. And for any entry of the matrix that is lesser than 0 or equal to 0, you assign it to 0. So what is the consequence of this? Let's say you've got some feature, right, in an individual unit in the first convolution layer. You're suddenly moving on to the second convolution layer, and you're passing that through a ReLU. that is the activation function, you will see that this particular feature that was there is no longer present because thresholding has been carried out. In this particular sense, that's what thresholding is about. So that's what ReLU is all about. Of course, there are different kinds of activation functions. You've got sigmoid functions, hyperbolic tangent functions, etc. So it's based on the requirements and how do you actually want to get the next layer. Following this, so you can have multiple such convolutions based on the extent to which you want to perform feature identification and extraction. Thereafter, you have to also understand that the computer is a device. It should also compute. So we've got a layer called a max pooling layer, an operation rather, where we reduce the dimensionality of a given input to something that's acceptable. But at the same time, it is important to ensure there is no loss of data. So if you take any image, you just draw the number 8, for example, on a piece of paper, you will see that the thickness of that number 8 is not infinitesimally small. Because why I'm saying this is because if you normally ask yourself a question, well, if I have 26 by 26 and I'm reducing it to 12 by 12, will there not be any loss of data? It's a good question. Well, ideally speaking, no. But actually, the answer to the question is both yes and no. Yes, there will be a loss of data, but the data that we are losing is actually a redundancy. Going back to that 8 analogy, the thickness is not going to be infinitesimally small, right? It's going to have certain thickness. And when you take pixels that are extremely small, such a thickness will span over more than one pixel. So the concept is that there is a fundamental assumption that the neighboring pixels have a strong correlationship with one another. And the closer the pixels are to one another, the more correlated they are. And the further apart they are from each other, the less correlated they are. So when I have pixels that are very strongly correlated with one another, I might be able to remove a redundant copy of the other. So that way, the advantage is I am reducing the net computational complexity and effectively ensure a dimensionality reduction. That is exactly what my max pooling layer does. It's a pooling layer that advocates an algorithmic approach called max pooling, effectively speaking, the maximum of the lot. So if you've got a matrix and you've got 4 regions, and each region in itself is a 4 by 4 matrix or a region, a sub-region, let's say, and taking the maximum of the values or entries from each of these sub-regions will in itself be sufficient to constitute the required set of steps here on. So that way you can save on a lot of space and you can save on a lot of computation. This is followed by a flattening of the data. So right now, it's evident from this diagram that we've got a 3-dimensional entity. So we've got to now flatten it into a unidimensional vector, largely speaking, and taking 12 into 12 into 64 will give you around 9216 such entries, and that would be flattened into a single unit. This would thereafter be taken care of by a set of fully connected layer. And it is essentially a layer of completely interconnected input and output neurons. Finally, you will have a softmax application. At the end of the day, our requirement is classification, which basically tells, well, you are giving me an input, and it is most probable that this input corresponds to this particular class. That implies we need to have a probabilistic description. So we largely apply a particular algorithm called softmax functionality, whereby you normalize the data. The outputs are going to be numbers. Let's say you have 5, 6, 7, 8, 9, and 10. It is important to note that if you have 10 output classes, there will be 10 output nodes. And each of these output nodes for a single epoch, as we call it, a single phase, will have one number assigned to it. Now, how do we normalize? If I take 1, 2, 3, and let's say I'm applying some function on these, let's say the exponent of each of these numbers divided by the sum of the exponent of all these numbers will give me a normalized quantity that scales only between 0 and 1. Of course, if you've got certain negative entities based on the values that we then assign, will go from -1 to 0. But taking the absolute value, it will only be between 0 and 1. Now, that fits into our understanding of probability as to whether it's a 0% chance, or is it a 100% chance, or is it somewhere in between, like let's say 95% chance. So a sample 4-layer CNN architecture has been presented here. In fact, it directly handles one of the elements of the demonstration that I shall be enclosing here with. An input image has been provided. Filtration, the convolution is in turn applied to constitute convolution layer 1. It thereafter has a ReLU applied on it and subsequent convolutions to constitute the second convolution layer. Another ReLU function, activation function, that is again. will in turn be applied on the second convolution layer data elements to constitute a max pool layer. We would thereafter flatten this data to constitute a largely flattened entity. This would thereafter be passed on to fully connected layers, and a softmax functionality would be applied to obtain the desired probabilistic values. So this is an overview of the sample process flow. First off, we feed image pixels into convolution layers to produce convol maps, the elements that constitute, in this context, the first, second, or nth convolution layer. We thereafter extend this sequence over the entire input image with multiple convolutions and multiple ReLUs in general. And effectively, we are bringing about feature identification. So we talk about with an individual image, and then we extrapolate our argument over the entire set. Again, the process of training and testing comes into play here. Normally, I train my data. I have to teach my network to understand that ultimately you're going to perform classification. And to perform this classification, I need to train this particular system. So I'll be feeding a lot of data to it. Why do I have to feed a lot of data? And especially when I, let's say, generate it over multiple epochs. By the way, it's important to understand that an epoch is effectively an entire pass over the entire bulk of the network. So when you've got a bulk of data and passing it along the length or allowing it to permeate along the length of the network one time, that is one epoch. So what happens after a single epoch is essentially, as I said, you will get these probabilistic numbers. Say you're giving a cat, but it then says, well, the probability of it being a cat is just 60%, but the probability of it being a dog is around 80%. That's a mistake. To us, it's a mistake, but for the computer, it's just learning. So what it does is that, again, it's important to understand there is a loss, right? There is an issue because the probability is completely off. So what it in turn does is calculate something called an error or error process. What it effectively does is there is a predicted label in the sense that if it's a cat, the probability value is tending towards a dog. So that's a predicted output. But then you've got the ground truth. The ground truth effectively says, well, no, this is a cat indeed. So how do you calculate the error between both of these using a mathematical algorithm and back propagate in turn, and thereafter adjust the values of weights and biases throughout the length of the network so that you can minimize the error at the end of the day. And this approach of back propagation, of course, is preceded by error calculation, and that can be generally brought about through a concept called as categorical cross entropy error based calculations, or entropy cross entropy based error calculation at large. So with that, the network would be able to adapt itself to the requirement which we expect of it in turn to perform well in. So once the feeding process is done, the extension process over the entire data set is done. As explained earlier, the bulk of the data, which is effectively three-dimensional, is flattened. Thereafter, an activation map is generated with reconstituted matrix values. Of course, by the way, flatten is also important. Reconstituted matrix values upon rectified linearization. Of course, it can be sigmoid functions, hyperbolic tan functions, etc. And of course, you've got pooling function, wherein you got convolved units, which are thereafter reduced dimensionally to make it much more computationally feasible. So this is an overview of the sample process flow. A quick insight. So I mentioned about updating the values of weights and biases. But again, we should not miss the bigger picture, because the bigger picture is that the network should train and adapt itself towards the requirement that I expect of it to perform really well in. But again, I can't go into each layer of a network myself manually and adjust its individual, let's say, weight towards making the final decision. It should be able to do that by itself. So a very brilliant or an extremely useful concept called as back propagation occurs. And again, that's where the error is calculated. And there is a back traversal or a backward directed traversal whereby the weights and biases values are going to be updated. But again, it's important to understand what is the ideal value of my weight and bias. So that's where an understanding of maxima and minima comes into play, because my ideal value of weight or bias will logically and naturally speaking be that value for which my loss is lowest. The lowest possible loss will be an ideal case, and I need to have a weight that is associated with that. So having a look at the graph here, for example, one of these local minimas or any minima in general could in turn suggest a value of weight. Let's assume that the entire graph is in the positive realm. You have a value of weight for which the loss is lowest. So what happens is we prefer that particular value of weight. But that's exactly where a problem arises, because you can have two kinds of minima, right? You can have a local minima or you can have a global minima. And normally, when a system traverses towards the entire set of possibilities, if your learning rate is not sufficient at the local minima itself, saying, no, I'm not going to go any further, well, right, it's not exactly accurate, is it? Because you've got a global minima over there, which is way better than this value. So your weight could as well be that value, which makes your system perform better. So this is exactly where hyperparameter configuration comes into play. You've got to set the value of learning rate, but not set it too high that it begins to oscillate and never converge at a result, nor set it too low such that the training rate becomes extremely slow and never gets the required value. So at the same time, there are other parameters such as batch size. How much of an input am I feeding into this system at a given point in time? So that is another example. And the number of epochs is also a good example, is also a very important hyperparameter. Again, an epoch is one complete traversal of the data set throughout the entire length of the network. And naturally, it makes sense, right? The more the number of epochs, the more the number of times my entire set of training data is going to pass through the entire network. And naturally, the robustness of this classification will increase. But there is one fundamental problem, that it will increase the computational time, it increases computational resources, and that might not be something we are always willing to afford. So based on our requirements, we set our epoch values and accordingly perform computation. So this is the technical side of things. Looking at some of the potential benefits that CNN deployment has, there are three, 4 points. First of all, translational invariance to distortion. This is extremely interesting in the sense, if I have an input image and I compare it with another image, which is essentially the image of the same object, but it's slightly lower, with the concept that neighboring pixels are strongly correlated, it would effectively be still able to generate the same result or classification for both of these at the end of the day. So that is one major advantage. Second concept is that the sharing of parameters. You use the same filter over an entire input image and multiple such filters over an entire input image or input images. So you effectively reduce the learning quantum or parameters. Thirdly, you can represent high-level features interdependent on another and perform learning capabilities. And fourthly, or by far one of the most important consequence of all, and thereafter handle large quantities of reserves of data, which might even so the current and prospective CNN applications. So CNN stands as a potent solution to classification challenges that especially involve imagery analysis. Some of the fields that employ and could prospectively include CNN on a larger scale have been enclosed below. So we've seen that CNN is highly suited towards classification challenges, right? Especially towards handling visual imagery based analysis. So some of the prospective fields include condition monitoring in the industrial front, for example. You've got a lot of mechanized components out there. You've got fault diagnosis and analysis, and that is a very prospective play arena where CNNs are largely being deployed. There's a lot of literature that goes on in this front as well. Secondly, autonomous driving. At the end of the day, it boils down to computer vision if you're using cameras. So taking these input images and feeding it to a network and asking it to make a decision and thereafter sending out actuation responses to the controller can also be one of the a critical application. Advanced driver assistance systems. It's not just self-driving cars out there. It could be any driver assistance system, such as adaptive cruise control, for example, that relies on cameras. Of course, you've got biometric authorization, authentication, face recognition, for example, biomedical imaging, especially. And of course, we've got logistical and warehousing, supply chain management, and entire linear based structuring, whether you want to have an identification of what is the box, where it is to be placed, or if you look at a box, what category, what kind of components can be enclosed inside to streamline the entire warehousing and logistics process. Again, it can be a very prospective CNN application. I shall now be moving on to a quick implementation phase, wherein I would be demonstrating a very quick understanding of CNN in practice over a very interesting or a very fun to use website, Playground of TensorFlow, and thereafter have a real use case demonstration of performing classification using convolution neural networks on an MNIST data set wherein we classify digits into one of many classes. So I shall share my screen a second. Just a minute. Yes. All right. Got it here. Perfect. I hope the screen is visible. So you can think of it a neural network here. And that's what the playground in TensorFlow is all about. You can actually learn and utilize and deploy your own algorithms in this website. And you can just play around just to see what every hyperparameter, what effect every hyperparameter has on the effective learning process. So you've got numerous features here. The ratio of training and testing data. Let's say you've got 10 input images, right? You normally set it as around 6 images for training and around 4, of course, 4 images for testing. So you can set that ratio here. So around 50%, so 50, 50, or let's say out of 10, 5 and 5. Or of course, you can increase the size also. Noise with respect to the amount of background information. So again, it makes your classification also a bit more robust with respect to any other form of spatial data that might be present apart from the input images. Batch sizes, again, the size of data that you want to pass through the entire network. You can set it to 2, 12, 15, 16, all the way to 30. So which kind of data set? Of course, you've got such a distribution, more of a radial understanding. Of course, you've got this lumped distribution. Again, a lumped distribution here also. You've got a spiral distribution as well. For the time being, we will go with a quick demonstration of this form of distribution. So again, we've got all these 5 factors on top. You've got number of epochs. This will be more of a real-time count. The value of learning rate. We will have the time activation function. We will set it to ReLU. Regularization, that is essentially minimizing the dropout of the system or the network so that it performs well for both the model that I'm training it on and for the input I'm training it on, and also give me good results to increase its generalization capability. Of course, I can choose one of 2 problem types classification, which we will go with. So we've got 2 kinds of data. You've got those represented by orange, those represented by blue. You've got numerous hidden layers here. I shall set it to 3 hidden layers. There'll be an output. And what are the properties that you in turn want to extract? So you've got x1, x2, can set this 3, 4, 5, 6. So I've got different kinds of features that I'm extracting, and all of these are in turn connected with neurons in the subsequent layers. Of course, the outputs are mixed with weights, and as with CNNs, of course, they are adaptive. So I can increase the number of neurons or decrease the number of neurons in any given hidden layer. This particular site allows me to work on these. So the number of neurons in the second hidden layer, the number of neurons in the third hidden layer, right? So one advantage, as you can observe, the value of the test loss and the training loss. So now that I have performed all these configurations, the learning rate, I'll set it to around 0.01 for now and perform the learning process. So as you can see, the classification is not entirely perfect, but it's more of it's, as you can see, it's distributed over a certain number of epochs, right? I have not preset a value of epoch, but then we can now see that the learning is more or less saturated. The test loss stands at around 0.02, 0.024, and training loss around 0.011, which is really good. More visually speaking, you can actually see that the orange is in its place and the blue is in its place. Of course, there are some misclassification instances here. And that again depends on the number of hidden layers and the other hyperparameters that you set.
So what if I change the number of hidden layers at a given point in time, right? What if I reduce the number of neurons? Now let us start. So how long is convergence taking? Or even forget about convergence. Is my final classification accuracy the same? So my system might not be as robust right now, or even if it is, the convergence to the final result might take a longer time. And the values of the testing and the training loss can also be observed. So I can thereafter play with the number of hidden layers, play with my activation functions, play with my learning rates also, and achieve the desired outcome. So this is definitely a great website to exercise our understanding of CNN. Moving on to the demonstration phase of this particular presentation, we've got a program developed using Python that focuses on digit classification. The dataset is taken from the MNIST repository. We've got around 60,000 training images, and we've got over 10,000 testing images. So at large, the program is divided into multiple sections for ease of understanding. Of course, my credits to Mr. Rajiv Ratan uh, for his impeccable explanation of this. The code is indeed with reference to his teachings. We import PyTorch, again developed using Python in the beginning. All the required packages, all the required functionalities are imported in the beginning. We've got to also understand that generally deep learning extends a reliance on GPU also. In other words, this actually stems from the fact that deep learning has an extended reliance on hardware or has hardware requirements, principally because if you take a look at the real world classification problems that arise, the number of learnable parameters will not just be in number in thousands or hundreds or even 100,000s. It will be millions or even billions at times. So to effectively handle all these learnable entities, to handle all these parameters, and to ensure that at the same time you give a good classification accuracy that is acceptable in general, is definitely a task that is computationally intensive, and you will require a lot of such convolutional layers, you will require a lot of such fully connected layers, and in general then a lot of neurons would be required, and this would in turn constitute a lot of computational expense, and that would mean naturally a heavier hardware requirement. So a system generally extends its reliance on the GPU unit of it, which is present as well, and not just on a CPU. So that's also an important aspect to understand, and that is something we are migrating to here also. Please note that the code has already been compiled and it has already been executed to generate results, because the training testing process takes time. Also considering the fact that there is network latency, because this is at the end of the day a cloud computing platform. Moving on, this is where we are booting in our training and testing data. So we have the train is equal to true, and we've got the train is equal to false. That suggests the testing data is to be put into train set and test set respectively. So it has been done successfully. Following this, we have a visualization in a matrix perspective of the different images. We've got again 60,000 image samples for training and around 10,000 for testing. And each of these images, whether they're training or testing, are 28 by 28 pixel sizes, and they're all of depth 1. That suggests they are of grayscale type. So we are just visualizing these here in a matrix format. And this is, of course, an overview of what we are going to classify. We thereafter prepare the train and test loader again. So we have the train loader, we have the test loader, we've got to boot it in. Following this is a chunk of code that is by far the most important section of this program, because this is exactly where we are constructing meticulously our convolutional neural network. We are especially carrying this out in the initialization function, because this is going to be called as soon as it's being instantiated. So evidently self.conv1 is equal to nn.conv2 the 132.3. That suggests that we are using 32 filters, 3 by 3 size kernels, each of these filters, and we use a value or a stride of 1 along with 0 padding. So the input images are filtered or convolved over to constitute convolved outputs that constitutes the first convolutional layer. Thereafter, we've got the second convolutional layer. Again, you've got operations of filters on them, and you now get an effective convolution layer, which has a depth of 64 this time, and the images would be of a different dimension, more or less 24 by 24, as we had seen from the slides earlier. After the second convolution layer has an output achieved,
we move on to the max pooling layer, wherein what is very important is to analyze the value of the stride here that naturally results in two things. Not only are we using max pooling that takes the maximum to reduce, okay, the number of parameters I'm using, but also I'm reducing the matrix's dimensional size. So I'm reducing that size by increasing my stride value, largely speaking. At the same time, do keep in mind that I can increase the matrix dimension by performing padding. As the name suggests padding, you just put some zeros around your entire matrix or such values or populated with values to get a certain dimension that you want. Following this, we constitute our first fully connected layer. In this fully connected layer, we've got, of course, the output, that is the units that are present in the max pool. That's having an effective size of 12 by 12 by 64. And now you're converting this or not converting, rather connecting it to a set of 128 nodes. Now, these 128 nodes are in turn connected fully to 10 output nodes. It's important to note that we've got digits from 0 to 9. That means we've got 10 output classes. So if there are 10 output classes, do note that there will be as many number of output classes as there are number of nodes, or vice versa, the number of output nodes as there are number of output classes. Following this, of course, we will apply a softmax functionality to give a probabilistic description. So of course, we've got to perform feed forward in the sense that the data should propagate in the forward direction. So we've got reshaping, flattening also, that's very important. So we've got an effective size of 12 by 12 by 64. And of course, we've got activation functions again, and we've got fully connected layers just being mentioned all throughout, and just an understanding that, yes, we've got to go in a feed forward sense. After this, of course, all the output of the resulting network is being presented here. This is an overview. We've got to, of course, ensure that the weights and biases are updated as explained earlier. So this is exactly where we've got to set our optimizer. We've got to ensure there's back propagation. After the entropy is calculated for each block, or cross entropy loss is advocated to determine entropy loss or loss in general for every epoch. So we are using an optimizer called an SGD. So remember when I mentioned that there is always that chance where you can get stuck in a local minima, and you can also have a possibility where you overshoot the global minima itself. So that is a trade-off that we have to achieve, and you've got optimizers that actually ensure this happens. So stochastic gradient descent is one such optimizer. We've got ADAM, we've got ADA Max, for example. All of these have functionalities that are suited for this purpose. Following this, we specify that our training should be extended over 10 epochs, and we extend our training process over 10 epochs. And all of this code ultimately points to just one thing. So you start one epoch, you can observe very clearly through the stack trace that the number of mini batches start off with 50 and proceed all the way to 450. And the loss starts off for the first epoch at around 2.262 with a test accuracy of around 56.16. But beautifully, the loss reduces to 0.355. That suggests that the learning is effective. The updating of the values of the weight and biases are very effective, and it gives you a test accuracy of over 91.46%. Do note, this is for the first epoch, and I am extending this over 10 epochs. So progressively, my values of losses reduce. Progressively, my value of test accuracy increases until it caps out for the 10th epoch for 450 mini batch size completion for a loss of 0.060 for a test accuracy of 98.100%. For training process. Now the training is over. Now that my first convolution neural network is trained and ready to be deployed, I now deploy my set of 10,000 test images from the MNIST dataset into my convolution neural network that I have just constituted. As you can see, the accuracy of the network on the 10,000 test images, is proved to be around 98%, which is commendable accuracy indeed. So this is again visualized. The progress in the value of loss and the progress in the test accuracy value is plotted by means of a graph here over the epochs. As you can see, the value of epochs keeps on progressing, the value of loss keeps on reducing, and the accuracy keeps on increasing and caps out at 98%, suggesting a decent convergence rate, or as it converges towards the target value. So this has been a quick overview on how do we perform a rudimentary classification on if I give a handwritten input image. That's how MNIST dataset actually is, a grayscale version, 28 by 28 pixel size input image. It can be the number 0. The process, or generally by intuition, it feels very simple because for a human being it actually is. But if we talk about how we extend that over a computer system being able to make the same decision, we now understand that it is indeed an entirely elaborative process.
So it is hoped that through the medium of this presentation, a high-level overview of what convolutional neural networks are all about, what is its current standing in the artificial intelligence domain, and of course, how we can execute a simple convolutional neural network over a cloud computing platform, and also play around with the different hyperparameters of a convolutional neural network. I hope all of this has been touched, at least at a higher level, and I hope to see you again very soon. Thank you.